Hi everyone, today we're going to be covering topic 4.9, oxidation, reduction, or redox reactions. So in topic 4.7, we very briefly learned that a redox reaction is a reaction where electrons are transferred between substances. In order to keep track of what loses an electron or what gains an electron, we'll assign them oxidation numbers. And generally, if a substance is oxidized, it will lose electrons. And if a substance is reduced, it will gain electrons. I know that this seems a little bit backwards, but the way we need to think about it is if something is oxidized, then its oxidation number goes up, right? It'll go up, and therefore it's losing electrons because oxidation number means more positive. As a reminder from the topic 4.7 video, elements, or anything in its natural elemental form, like O2, for example, or I2, for example, I'm going to refer to it as ox number. Its oxidation number is always equal to 0. For monatomic ions, or just ions with a single atom, its oxidation number is just equal to the charge. For fluorine, its oxidation number is equal to -1. For oxygen, its oxidation number is equal to -2, unless it's peroxide. Then in that case, it is -1. And finally, for hydrogen, its oxidation number is equal to +1, unless it's a hydride, then it is -1. And the most important thing to remember is the sum of oxidation numbers in a neutral compound is equal to 0. The sum should be equal to 0 if it's a neutral compound. If it's an ion, then the sum of oxidation numbers will equal the charge of the ion for a polyatomic, for example. So anytime we have a redox reaction, we have what are also known as half reactions. So oxidation and reduction reactions are typically balanced separately. And so let's take, for example, the reaction of tin ions, Sn2+ aqueous, plus Fe3+ aqueous, reacting together to form Sn4+ aqueous plus Fe2+ aqueous. For this reaction, since it's a redox, we should consider what is being oxidized and what is being reduced. And so if we look at tin, its oxidation number is going up, and so it's being oxidized. For iron, its oxidation number is going down, so this is being reduced. So if we take the oxidation reaction, for example, oxidation means it's losing electrons, and so Sn2+ will react, essentially, to form Sn4+ plus 2 electrons, because it's lost those 2 electrons. For the reduction reaction, we have Fe3+ aqueous reacting with 1 electron in order to make Fe2+, right? Because it's only gained 1 electron. Now, if we look at these, the next thing we need to do is balance the electrons. So if we look in our top reaction, I have Sn2+ goes to Sn4+ plus 2 electrons. In the bottom, I only have 1 electron, and so I should add 2 to the electrons. And if I add 2 electrons, I should add 2 to everything in order to balance out this equation. What is most important is that we balance the electrons in both the oxidation and reduction. So now I'm going to give you a list of steps, all in order for balancing half reactions or balancing redox reactions in order. Number 1, we're always going to assign oxidation numbers to everything in our reaction. Secondly, we're going to write the oxidation and reduction half reactions, similarly to what I did on that last slide. So first, we'll balance the half reactions for atoms. Secondly, we'll balance the half reactions for charge by adding electrons. Once we have those balanced half reactions, we make the electrons lost equal to the electrons gained by multiplying the whole reaction, the whole half reaction, I should say. After that, we put the coefficients or the numbers in front of the atoms or molecules into the reaction, then balance the remaining atoms. Important note here is to not change the coefficients of species involved in the redox. You'll see what I mean more on the next slide. The last step, number 5, is to check to make sure the total charge is the same on both sides. Once you do all of those steps, we should have a nicely balanced redox reaction. So I want us to work through this little bit of a practice problem together so we can understand how we actually balance half reactions for a redox reaction. So I'm going to take this overall reaction here, copper plus aqueous plus iron solid makes iron 3+ plus copper solid. Step 1 is oxidation numbers. So if I'm going to do that for any monatomic ion like copper plus, the oxidation number is just equal to the charge, so that'll be +1. For any elements, iron solid, this would be 0 because it's in its elemental form. For 3+, its oxidation number, for iron 3+, its oxidation number is +3 because its charge is +3. And for copper solid, again, it's 0 because it's its elemental form. Step 2 is the half reactions. So we're going to split these up into the oxidation and reduction reactions. If we look here, our copper is losing, or it's gaining an electron, or it's losing its oxidation number, and so that is being reduced, and our iron is what's being oxidized because we're losing electrons or we are gaining more oxidation number. And so in our copper, we have copper plus aqueous, and that is gaining an electron because it is being reduced, and that'll make copper solid. So this is our reduction. And for our oxidation, our iron solid is reacting to form iron 3 plus aqueous, and it is losing 3 electrons, right? Because we go from neutral to 3 plus. So step 3 here is to balance our electrons. If we look at our first equation, we have 1 electron. If we look at our oxidation, we have 3 electrons. And so what we'll need to do here is multiply the entire top equation by 3. And so now our half reaction should be 3 Cu plus aqueous plus 3 electrons goes to make 3 copper. And then the bottom reaction will stay the same. Oh. So now our electrons are balanced. Step 4, add your equations together. Now that we have our balanced half reactions and our electrons cancel out, we can add them back together. And so what we'll have is 3 copper plus Fe solid will react to make Fe3 plus aqueous plus 3 copper solid. We got to also remember that since we're adding them together, we should have 3 electrons on this side, and we have 3 electrons on this side. But of course, since the electrons show up on either side, we can cancel those out. And so now we can write, of course, 3 Cu plus Fe solid makes Fe3 plus 3 copper solid. Now, if you do this and then your number of electrons don't cancel out, then you need to go back and multiply your half reactions to make sure the electrons are equal on both sides. Now, step 5 is to check total charge. And so on our left side, we have 3 times plus 1 plus 0. That should be equal to 3 plus times 1, because we only have 1, plus 3 times 0. Of course, 0 and 0, those just equal 0. So we should have plus 3 equals plus 3. And so this would be our balanced redox reaction. So let's work on one more practice problem together for the standard redox reaction. Here we have a reaction between aluminum and zinc 2 plus, aluminum going to Al3 plus, and zinc plus 2 electrons going to zinc solid. And so we already have the half reactions written for us between aluminum and zinc 2 plus. So it's saying based on the half reactions, what is the coefficient for aluminum if the equation is balanced with the smallest whole number coefficients? So we already have our half reactions here. If we look at the number of electrons here and there, we have 3 electrons for the aluminum half reaction, or the reduction, the oxidation here, because we are losing electrons, and we have 2 electrons for our reduction reaction. And so if we want this to be equal, what we can do is we can multiply this whole reaction by 2 to get 6 electrons. We can multiply this whole reaction by 3. And so we should get 2Al solid goes to make 2Al 3 plus 6 electrons, and 3 zinc 2 plus 6 electrons reacts to form 3 zinc solid. And of course, we're asked for the coefficient of aluminum solid. And so if we look here, that coefficient is 2. So our answer should be B2. If you were to combine these and form and give me the entire redox reaction for aluminum reacting with zinc, it would be 2Al solid plus 3 zinc 2 plus react together to form 2 aluminum 3 plus ions plus 3 zinc metal. A variation of balancing half reactions is balancing half reactions in acidic conditions, which we might see in the future, and is a little bit more complex, but I think it's interesting for us to talk about and learn. And so in this reaction, we have chromate and dichromate anions, Cr2O7 reacting with chloride ions, Cl to form chromium 3 and chlorine gas. And so in a reaction like this, we can still split up our half reactions like so, right? And so for one reaction, we should have Cr2O7, O7, 2 reacting to form chromium 3 And in our other reaction, we have Cl reacting to form Cl2 gas, right? That's just splitting the reaction up into its constituent parts. Now, we're told, of course, that this is done in acidic solution, and so to whichever reaction has oxygen, we add H plus to the reactants, and we add H2O to the products to help us balance it. And so if we take our chromium oxide, that's where the oxygen is in this reaction, we can do H plus Cr2O7, 2 will react together to form Cr3 plus H2O. Now if we balance this equation, we can balance the chromium by adding a 2 in front of Cr3 plus. We can balance out the oxygen by adding 7 H2O, and then to balance out the hydrogens, we should have 14 protons or 14 H plus ions. Next thing we want to do here is balance our charges. And so if we look on our left side here, we have 14 times +1 plus 1 times -2. That should equal 2 times +3 plus 7 times 0, because H2O doesn't have a charge. And so this will be 14 minus 2 is equal to 6. So on our left side, we have 12, or plus 12, and on our right side, we have plus 6. In order to balance this out, we can add 6 electrons to the starting, or the reactants. So if we're going to balance our charges, we should have 6E- plus 14H plus Cr2O7 2-. That will react to form 2Cr3 plus 7H2O. Okay, now that we've balanced out that first half of the reaction, right, this would be our reduction since we are gaining electrons. We can balance the oxidation portion of the reaction. So we have Cl- reacts to form Cl2 gas, and this is aqueous. First thing we need to do is balance out the atoms, so this would be 2Cl- goes to Cl2. Then we need to think about our charges. And so we have 2 times -1 should be equal to 2 times 0. And so -2 is equal to 0. In order to balance out this oxidation reaction, we should add 2 electrons to that side of the reaction right there. Now, of course, we need to balance our electrons between these two half reactions. In order to do that, what I should do is multiply this entire oxidation reaction by 3 to have the same number of electrons. So if I go ahead and do that down here, I will get 6Cl minus reacts to form 3Cl2 gas plus 6 electrons. Finally, I have my two half reactions and my electrons are balanced, so I can add them together while canceling out the electrons. And so finally, this balanced acidic reaction should be 14H plus 6Cl minus plus Cr2O7 2 minus will react together to form 2Cr3 plus 3Cl2 gas plus 7 water molecules, and that is a liquid. If I zoom out, that is my entire balanced acidic half reaction. So under acidic conditions, we would have H plus and H2O present. We'll have a little bit more practice with this in class, but for now, that's all. Thanks, guys.